Have you ever stopped to think about how an elevator knows exactly which floor to go to? Or how a factory assembly line coordinates all its robotic arms perfectly? You know, it's not magic. Not at all. It's actually a set of rules. A really simple language that lets machines make decisions. And today, we're going to learn that language.
All right, so we're about to pull back the curtain on the hidden brains that power industrial automation. We're going to start with something super simple, a basic switch, and build our way all the way up to the powerful little computers that pretty much run our modern world. Okay, here's our game plan for today. We'll kick things off by figuring out what relay logic even is. Then we'll learn its visual language, which is super cool. After that, we'll meet its modern replacement, the PLC, see exactly how it thinks, and finally, we'll connect all these ideas to see how they work in the real world. Let's dive in. So let's start at the very beginning with the core concept, relay logic. See, long before we had microchips and computers, we had these clever circuits made of electromechanical relays. And these were the OG building blocks for making any kind of automated decision. So what in the world is a relay? Well, it's actually brilliantly simple. Just picture a light switch. But instead of flipping it with your finger, a tiny electrical current flows through a little coil of wire, which creates an electromagnet. That magnetic force is what physically flips a switch on a totally separate circuit. And that circuit can be controlling something way more powerful, like a huge motor. So it's a way for a tiny small signal to control a great big action. Now, you could draw these circuits using a normal schematic, kind of like what you see on the left. And it's totally accurate, but man, does it get messy and complicated really fast. So to make things easier, engineers came up with something called the ladder diagram, which you see on the right. Notice how it looks like a ladder? The two vertical rails are the power source, and each horizontal rung is its own little circuit. It's just so much cleaner, simpler, and it quickly became the standard for the industry. So how does this language of ladders actually work? Well, it's about more than just drawing circuits neatly. It's about creating logic. This is where we start building the actual rules for our machine to follow, just by combining these simple relays in different patterns. And this brings us to our most basic, fundamental rule, the AND function. Take a look at this rung. For electricity to flow all the way from the left rail to the right, the path has to be totally complete. What that means is switch 1 and switch 2 must both be closed. If even one of them is open, the circuit's broken and nothing happens. Simple as that. The other fundamental rule we need is the OR function. See the difference here? The switches aren't in a line anymore. They're in parallel. This creates two possible paths for the electricity. This means power can get to the end if you close switch 1, or if you close switch 2. You don't need both of them. This gives our machine a choice, a little flexibility in how it makes a decision. Okay, so wiring together these huge panels of physical relays totally worked, but it was clunky, it was slow, and honestly, it was a nightmare to change or troubleshoot. The industry desperately needed something better, and that brings us to the modern brain of automation, the programmable logic controller, or as everyone calls it, the PLC.
This quote right here just nails it. The whole goal was to take all of that complicated physical wiring and turn it into software. PLCs were designed from the ground up to be faster, way more reliable because there are no moving parts to wear out, and the big one, they're incredibly easy to modify. Instead of spending hours rewiring a massive cabinet, you just rewrite a few lines of code. It's a total game changer.
And this is what one looks like in the real world. A PLC is basically a tough, rugged little industrial computer, and inside this box, there are no actual relays clicking open and shut. Instead, it runs a program, a virtual relay circuit that does the exact same job, but it does it at the speed of light. So how does a PLC actually think? Okay, this is where it gets really, really cool. We're going to look inside the PLC's programming and literally watch it make a decision step by step as we flip physical switches in the real world. Okay, let's watch this thing go. Right now, neither of the buttons is being pressed, so the PLC's little input lights are off. But wait, look, the output light is on. That's because the program running on the right is telling it to stay on as long as the inputs are off. Now, let's see what happens when we change that.
All right, I'm pressing the first button now. The PLC sees that input turn on, and you can see in the program that the first virtual switch highlights it closes. But the path for the signal, it still isn't complete, right? The logic needs something else to happen, so for now, the output light just stays on.
And here it is. This is the magic moment. I'm pressing the second button. Bam! Both of the PLC's inputs are now active. And in the program, you can see the path is finally complete. That energizes a little virtual coil, which then flips a second switch in the logic, breaking the circuit to our output light and turning it off. We just watched a physical action trigger virtual logic to create a whole new physical result. How cool is that?
Now, controlling a little light with a couple of buttons is a fantastic example for sure, but the true power of a PLC comes from the huge variety of sensors it can use for its inputs. These are its eyes and ears on the real world.
So instead of a person pushing a button, that input could be a pressure switch that closes when a tank gets full. Or it could be a level switch that activates when a liquid hits a certain point. It could be triggered by temperature, by flow, or even a limit switch that tells the PLC a robot arm has reached the end of its path. Every single one of these sensors is really just a simple switch, feeding a simple on or off signal to the PLC, and allowing it to make some incredibly complex decisions about the world around it.
So there you have it. We've gone all the way from the simple physical click of a relay to the silent, lightning-fast logic of a PLC. We've seen that deep down, automation is built on a simple language of ands and ors, of open and closed paths. It's a language that lets us give very specific instructions to our machines, which kind of leaves us with one final thought. Now that you understand this language, what decisions would you teach a machine to make?